Hey, welcome back to our fourth episode of this series. We're one quarter through the currently planned episodes. Episode 16 will be a review of everything we did so far, as well as looking forwards for where the community wants the series to go next. So look forward to that. It's been a while since the last episode. Since recording that episode, Godot version 3.5 has had its first official release. So to start, we are going to go over how to upgrade to a new version of Godot for your project. Generally, along the 3.x versions, upgrading is fairly simple. Going up to the 4 versions will require using the upgrade tool that I expect will be integrated into the early versions of 4. If you're using Godot directly as an executable, you just need to download the version from the website and run it, just like we did when we first installed it. From that launcher, you should be able to open your project and see if any bugs appeared. If you're using Hourglass, it's even easier. First, you can download the version you want. Make sure it's the mono version as well. Then go to Edit the Project Launcher entry. Change the launch version to the version you just installed. Now, when you launch the project, it will use your chosen version. Make sure to check if any errors popped up so you can try to fix them. Theoretically, going from a release candidate of 3.5 to the official release shouldn't have any errors, but double check just to be sure. Also, a point of interest that you might have noticed is that my desktop has changed a lot since the last episode. I was originally using a custom Kubuntu, so KDE, desktop layout, and I've actually switched to a preset global theme that is supposed to be very similar to Apple's, and I find it very comfortable to use, but still have the backend and systems of Linux running. And so I didn't switch to a Mac suddenly. This is still Linux. Alright, so now that we have the project up, we're running 3.5 stable mono. We can build. And you can see we have no errors, and there's no errors in here or in here. And if we run the project, you can see that everything's working normally. So from the last episode, I actually made an unintentional error. Or rather, I introduced an unintentional feature that could severely impact the play experience. And I can show you what I mean. As long as the player only moves the mouse in reasonable ways, the controller looks pretty normal. But if you try to look up too far, they can actually flip their camera over and continuously rotate. This is because we forgot to clamp the X rotation. In order to fix this, we need to add an extra alteration. And so we'll add the following to our input function. Now we have to do it this way because the rotation degrees is actually a C# property, so we can get and set it directly, but the individual values on it cannot be directly modified. So all we have to do is store it as a local variable, make changes to the local variable, and then set the rotation degrees to our modified local variable. It can look a bit clunky, but it produces the desired result. And a bonus is because we're doing this in the input method, it will only do clamping calculations when the mouse is moved. Like what we learned in the last episode, this is an event-based method, so it will do nothing if no events are processed. Now, this episode we are going to be working on jumping and sprinting. Some of you may have already added sprinting in the homework back for episode 2. Additionally, the jumping will require us to simulate, or rather emulate, gravity. I'm going to base this off of an amazing GDC talk by Kyle Pittman called Math for Game Programmers, Building a Better Jump. It's a great talk, and it's only 25 minutes. I'll link it to you in the description if you want to check it out. Because the talk is very comprehensive, I'm going to gloss over the explanation of why and how the math works, and focus on the equations that matter for our usage. Briefly, I will say this. Pittman's talk handles jumping in a 2D space, but extrapolating the math into the third dimension is fairly simple. Now first, we're going to want to add some export variables. And now we're going to introduce 2 new private member variables. So the exported variables are going to be the floats for the desired height and distance traveled when jumping. And the member variables, gravity and jump initial velocity, will be calculated and used to produce the desired result. we'll do the calculations in the ready function so that the heavy math of this is only ever done once. I simplified the equation so that it's easier to type when it comes to programming, but feel free to reference Pittman's talk if you want to see the math as it is in mathematical notation, because that'll definitely help you understand what's going on and why different elements are where they are. And so those two equations will set the properties for gravity and jump initial velocity. And it's happening in the ready function, so it'll only happen once, and then we can reference them in every process or physics process function that we desire. We're going to be applying these values in the process function, because if we put it in the physics process function, and the physics step is a different rate, the player may experience some latency. And so this way, the velocity is only ever being applied during the physics step, and so it will be very consistent regardless. And when we apply it here, this will always be based on the frame rate, which theoretically should be higher than the physics step rate. So after we've applied the normalization and speed functions, we're going to set the target velocity back to the original velocity's y value. That'll keep our jumping calculations on a separate value completely from the x and z movement. Now, after our lerping functions, what we'll do is we'll do first the gravity application. Now, what this function does here is it uses the built-in Godot system for determining if a body is on the floor. Because we have vector.up as the value here, if the physics body is touching a surface that has a normal vector close enough to this vector, it will decide that that's a floor, and it'll allow us to use this to check for those kinds of surfaces. The degrees value at the end here determines how close a surface has to be considered a floor. And if it's bigger than that, it may consider it a wall or a ceiling. And so there's built-in functions to determine if it's touching a floor, a wall, or a ceiling. And based on that, you can apply some logic. For example, we're only going to apply gravity if we're not touching the floor. And what we can do now is if we are touching the floor, which would just be else, we can set the velocity.y to 0. And what that'll do is it'll reset so that if you have a lot of gravity being applied and then they touch the ground, the next time they jump, the velocity.y will still be very, very negative. Or if they fall off a cliff, it'll fall a lot faster than you would expect. And that's not going to be very good. Now we're going to make a big if statement for jumping because there's a few things that we want to check for. And so the first part of this is we want to make sure they're actually pressing the jump button. The second step, we're going to check that it's on the floor so that you can't jump in the middle of the air. Next, we're checking if the velocity.y is less than 0. This means that either they are currently falling or they're on the ground. What it means is they are not trying to jump at the moment. And then if all of this comes out to be true, we will set it to the jump initial velocity. And so that motion will be theoretically instant. What's interesting is because we're setting the target velocity.y to the velocity.y, when we do our linear interpolation, it does it by element. And so the y value actually is unaffected by the x and z. And so the x and z will smoothly interpolate to their new positions, whereas the y will remain where it is based on our calculations here. If you wanted to be even more efficient, you could actually break the x, y, and z components down and have the interpolation be applied to a vector 2, and then do the y calculations on its own. Personally, I find that solution a bit too verbose, and this is pretty easy to understand what's happening for the most part. Now, I'm going to take a brief moment to discuss this jumping code here. The code we did here should produce a perfect parabola jump. Because we're in a third-person view, it is very difficult for the player to actually visualize their jump. In the video, Pittman explains how to add more dynamic approaches to jumping, such as holding the button to jump higher or falling faster when the peak has been reached. I'm not covering them here since Pittman explains the approach very well, and if you're following along, you should be able to implement the systems he describes. I personally don't believe they're going to be terribly helpful for this first-person game. In a 2D game, it's a lot easier to see how much the player is jumping, whereas in first person, it's a little more difficult. And so it's easier to make something regular and understandable like a parabola, as opposed to a more dynamic system. Now, if we want to test our results here, we can see that we made a big problem. So first off, our debugger is going crazy because the input map action jump doesn't exist. That's because we never went into the input map or made a jump button. So we'll make it there, make it a spacebar. I don't believe physical is required. I believe most keyboards have the spacebar in the same spot, but I want to just be sure. That'll fix that error. And then the other one is that we're floating up. And so what that means is we're subtracting a negative value. And so we could change this to be a positive 2, or we could just be adding gravity. And that's what I'm going to do, is I'm going to choose to add it and store it as a negative number. That way, if you wanted to invert it, it'll just increase, and you can invert it back and forth to change the direction of gravity. I would recommend that be a more advanced extension of this, because doing that kind of thing, you'll also need to be changing how you check for the floor and a lot of other issues. And so you'll need to be checking the move and slide. But that is a functionality that you could create with a more dynamic gravity system. And so now if we save, we'll try to run it again. And now we're falling. And so the problem here is we don't have any collision. If you can see this, there's no colliders on these boxes here. Now, there is the option here to use collision. And now it should generate colliders. And as you can see, we're not falling. We can move around and kind of slide over, and we can jump. Now, this isn't that fun, and this level was originally made just to be sure that we're looking and moving around properly. And so now that we have gravity and jumping implemented, it's really important to consider how we want to contain the player. There's a couple different approaches to this. You can have the levels exist as islands in a void, but you'll need a way to determine if the player has fallen out of the map and then automatically kill them or respawn them back onto the last valid platform they stood on. For the games that I like to make, the players are contained in a contiguous physical space, and usually there's cleverly placed props, structures, or other elements that prevent the players from falling out of the map. Because we are focusing on concepts, not art this series, I'll be demonstrating this with making really high walls. There is the option to make these walls invisible using custom materials, but that is up to your preference. For this, we're going to need to go back to our CSG nodes and build them a bit bigger. Something that we can do better this time is to check the player size as well as the jump parameters we assigned to properly design this level. This will help us plan out certain elements that the player can interact with. So first, we want to make a big box that determines the space the player can interact with. This is fairly easy. We make one big box, and then as a child of that, we can make a smaller box that's set to a subtract mode. And so for this, I'm just going to call it the main hull, because it's the main box that's going to contain the player, and then we can put interesting objects inside of it for the player to interact with. Now first, what I'm going to do is look at the player controller. Our max jump distance is 2 and the jump height is 1. That means that theoretically the player should only be able to jump on a box that is less than 1 unit high. In Godot, we like to think of these as meters, and so 1 meter high and 2 meters far. Depending on the person's athletic ability, that might be a bit extreme and that might be very easy. And so I'm going to configure the snap to be 1 meter on all axes. That way, when we move positions, we're making sure to move by 1 meter, and we can see if the player will be able to jump that high, and if they will be able to jump that far of a distance. And I'm going to make a spatial to hold all of the different interactable props. And we can keep it exactly where it is, and then add other CSG nodes as children. Make sure to set use collision on them if you want the player to use them. And you can see that it's snapping. And so you might notice it's a little difficult to see everything in the scene, mainly because everything's using a default white texture. There's no sun in this, and there's no information otherwise. So what I'm going to do first is add a sun called a directional light in Godot. Can move it up, and we're going to rotate it. This arrow here, if you can see it, points where the sunlight goes. And so we're going to angle it down and turn. You can see it's very bright there and darker there. Then in directional shadow, we have all of our directional shadow settings. I'm going to set it to be PSSM2 splits. That's a little bit faster than 4, but usually not necessary. And then make sure under the light settings, we want shadow enabled. And now we can see shadows of the different objects in the scene. And so we can see easily, without checking, that this is barely above the floor. So if we hold Control, we can put it directly on the ground. It's still not perfectly accurate, as you can see. This little chunk here is missing. Under the light settings and shadow, you can choose the contact setting to increase the connection. As you can see, increasing it just a little bit snaps to that corner to make it look perfectly accurate. It does produce slightly blurry fringes when you're looking at it from other angles. And so what's recommended is to try to tweak it a bit to make it look as realistic as possible while still having that precision looking close. So it looks fairly precise when you're looking close up. And it starts to fall apart when you're looking at it from far away. You can see it flicker in and out. And so that's something you'll have to choose for yourself, what you care about. You could turn it off completely and just have the slightly offset shape. You can turn down the maximum distance so that shadows only happen very close to the camera. You can blend between the splits, which I like to do. Using 4 splits will be more accurate. Another solution is to change the normal bias. And so as I can see, setting this to 0 will actually be very close to accurate. Just a small wedge there, but for the most part it's not too noticeable. This box here is 4 meters tall because the height is measured from the center outwards. And so if we set that to 1, which we can't, if we set it to 1, this is now 2 meters tall. We've set it to 0.5 to make it 1 meter tall. And so theoretically the player can jump onto this and not this. And so something that's fairly important when doing these mathematical calculations is to test, to make sure that what you believe is correct is correct. Sometimes it's because the math was interpreted incorrectly, sometimes you have something else wrong, but I'm going to test it here with these two and see what the results are. And so what I'm able to see is that jumping this way still gets us to that 2-meter high block. The reason we're able to jump that high is because this, for some reason, is actually double what we need. And so in the code, to make it consistent with the values it's producing, what I would do is I would go and divide that by 2. And so I could integrate it into the equation here, but also we can just put it first in front. And so that'll divide the jump height by 2 and then perform the calculations as normal. I also added a few more to show what's going on here. So we're able to jump to that height. This is 2, so we're able to jump to that height. We're not able to jump to 3. But as you can see, when we jump to 2, it kind of slides over first. See, what's happening is because we're using a capsule collider, the player has these round edges at the bottom. And so if the round edge catches on the ledge of the surface, the player is able to stand on it and walk up it. Now, if you didn't want this, what you could do is take the collision shape and change it to be a cylinder. There's a few tweaks you'll need to do. You don't have to rotate it as a cylinder, and then you're going to want to change it to be the right size for our capsule here. And now if we go back in to test it, we can go here. Walking up against it won't let you crawl up it because the cylinder is solid. You can jump up 1 meter, but you cannot jump up 2 meters. Now, personally, I prefer the capsule shape because that allowance to just miss a jump and still make it up to the ledge, I think is a little more forgiving. And I like to have that, especially for games that I expect the player to be moving fast. You want to be forgiving in their inputs. And so I'm going to reset this back to the capsule. I'm also going to change the jump height. I want to be able to jump up 4 meters. And the distance, I think I want to be able to reach the same. And so now, when we jump pretty high. And we can make it up to this top one. We even jump a little bit above it. And because we have the capsule, these slight ramps will stop us for a second, but we'll still go up without jumping. And we can fall pretty smoothly there. Now, at this point, the controls probably feel a little bit floaty. And that's okay, because what you need to do is you need to manipulate the different properties in the player controller to get something that feels good to you. And that might take a little bit of time, but tweaking it and running it and tweaking it and running it is going to be your best friend. Now, a quick hack that I would like to add that gives the player a little more control would be to allow the player to stop moving upwards as soon as they release the spacebar. Because we're applying gravity every process frame, all we have to do is set the velocity's y component to 0, and then the player will start falling that frame afterwards. Now, in this if statement, we're checking that it was just released, which means that the player just let go of the jump button. They're not on the floor yet. Check if the velocity.y is above 0, which would mean that it's positive. So they're still moving upwards. Velocity.y does 0. And testing it out just briefly, it feels immediately more responsive than the regular jump parabola, mainly because as soon as you want to fall down, the player will start falling down. And all they have to do is hold it to reach the higher heights. But if they just want to do a small jump, they can do it. Now, running at the same speed all the time can be a bit of a drag. So what we're going to try to do is add sprinting. For sprinting, you may have guessed that we can just decide between 2 different speed values, depending on whether the sprint key is currently pressed. For this, the code is actually really simple. We just need an export variable to store the sprinting speed. This way we can change the sprinting speed independently from the walking speed. Additionally, we need to consider if we need to revise the jumping code. If we set the maximum jump distance to a specific value, and then the player is sprinting on the jump, they could reach up to double the distance we expected, as opposed to the exact distance we calculated for. However, this will make walking jumps travel a shorter distance than what they currently are using. If we were feeling incredibly fancy, we could calculate variance of gravity and jump initial velocity for walking and sprinting, and then switch between each on whether the player is sprinting or walking. It would then force the jump to always cross the same distance and reach the same height whether they sprint or walk. However, I would consider this a more advanced system for what we're trying to make, and so I'd rather relegate it to a later episode if we so desire. Specifically, I would prefer to design this kind of behavior using a behavior tree, which we'll be going over starting in episode 10. For now, we're going to be going with the assumption that sprinting is the maximum speed and distance, and so we need to use our sprint speed in the calculations for gravity and initial jump velocity. For setting up the speed change, we first need to add a sprint input action in the Godot editor, and for me, I'm going to set it to be shift. And now we're going to set our export variable for sprint speed, and I'd like to set it below speed directly, so it'll show up next to each other in the editor. I copied over from the speed because I wanted to use this same export property range. That way we'll get the slider for sprint speed as well to make it easy to manipulate. In the ready function, instead of using speed here, we're going to use sprint speed. And then down in our process function, we're only using speed right here. And so what we need to do is we need to determine whether we are currently sprinting or not. So I'm going to introduce a local variable called current speed. And so current speed is going to be equal to speed. And then if sprint is currently pressed, current speed is equal to sprint speed. And we can even remove the curly braces, make that a little more concise. Now we can use current speed instead of speed. And so then when this is manipulated, it'll change whether or not we're pressing the sprint button. Now in the editor here, what I'm going to do is I'm going to increase the sprint speed because right now they're the same value. I'm going to crank it all the way up to 10 just to make the difference super obvious. And so as you can see, walking normally and sprinting are very different. And what's nice is because we're already interpolating the speed values, we are still, and you can see my shift and jump on the screen keys. Because we're interpolating our velocity on the X and Z axes, you actually get a smooth transition from walking to sprinting. And so if you wanted to do one of those AAA, generic, gritty, realistic, big quotes, character controller, you could make sure that your acceleration is a fairly low value, and moving from regular walking to sprinting would be a slow, gradual change. And then you just want to make sure you have an animation to show that interpolation as they speed up, like a regular person would when they start running. Except for maybe Olympic sprinters. Now, something I believe is very important to consider with any feature you're adding is whether or not it's desirable in your project. If you look at the original Halo trilogy, sprinting is not something the player does, and the game doesn't even suffer from this in any way. Even when sprinting was added in Halo Reach, it was initially considered a special ability, not an innate feature. I'm taking this trip down memory lane mainly to illustrate that I'm old, and also to show that just because a feature is in modern AAA games doesn't mean you have to have that in your game, and your game won't be worse just for not including it. It's an important design consideration that isn't something I can really give you the right answer to, because it depends on the kind of game you want and how you want the player to experience your game. For this episode, your homework is to make a small shooting range level. You can style it any way you want. I personally prefer arena style, like in Quake, but if you want to go for some cramped hallways or even a realistic gun range, This homework is to help you practice putting scenes together with a goal in mind. Because we know how the player is able to move, we can put platforms, ramps, etc. throughout the level for them to move around on. So in our next episode, we're going to start creating some simple weapons. And this homework will give you a good place to test the combination of moving and shooting in the game. I'm sorry if it didn't feel like we covered a whole lot in this episode, but what we did cover will likely be the basis of our character movement for the rest of the series. It will shape how players interact with the game, which is really important for the level design. This series is supported by my members on Ko-fi. You can join them in getting early access to my videos for as little as $1 a month. My current supporters are Noel, Miguel, Grabhoon, and Cody R. Thank you so much for your continued support. You're helping make my dream a reality. And thank you so much for watching. I hope you're enjoying this series so far. If you want to get real-time updates on my projects, you can go follow me on my Twitter, @ofsquiggles. I'll make posts there about my important Ko-fi posts that are available to the public, so look forward to those.